To turn a standalone computer into a workstation on a network, you're going to need some special software. For a start, you'll probably want some sort of application software. Perhaps an email client, so you can communicate with other people, a web browser for viewing your intranet and surfing the internet, or a file manager so you can copy and move files from one place on the network to another. You're going to need some programs to control your network interface card, the so-called drivers for this device. And you're going to need some special software to manage the way that data is sent and received on the network. Software to implement the rules of data transmission, the so-called network protocol. Already you can see an important concept when it comes to networking software, the concept of software layering. Very broadly speaking, there are 3 layers of software between the user and the network. Each layer can communicate with whatever is directly below and whatever is directly above. You'll hear more about the advantage of software layering later, but for now, let's say more about the network protocol. Strictly speaking, a network protocol is a set of rules to govern the way that data is packaged, transmitted, and received over a network. But the software that implements and enforces these rules is what we usually refer to as the protocol. Only devices that share a common protocol can communicate with each other on a network. In a sense then, a protocol can be thought of as the language that computers speak to each other. Just like us, computers need to speak the same language in order to understand each other. There are lots of different types of network protocol available, but TCP/IP is the most well known because it's the protocol used by the internet. But TCP/IP is not just for the internet. It's also widely used in private LANs and WANs. As you'll soon see, TCP/IP isn't just one protocol, it's a group of protocols, and therefore a suite of programs. One of the key features of a network controlled by TCP/IP is that packets of data are forwarded through the network by routers. Here you can see a large segmented network with several interconnected routers. Typically, each user's computer is connected to an Ethernet switch. In fact, between any pair of routers there may be an extensive subnetwork with one or more switches. The routers are therefore gateways between these subnetworks. But let's look at the bigger picture for now. Imagine a document is being copied from one computer to another. The first job of the protocol on the sending computer is to break it up into smaller data packets. Each packet contains a portion of the original document. This is known as the payload of the packet. Each packet is given a sequence number, so they can be reassembled in the correct order at the other end. The protocol will also calculate a value based on the data inside the packet, the so-called checksum, and this will be added to the packet too. Each packet is also given some addressing information, so the routers know where to send it. To get across each segment of the LAN, each TCP/IP packet needs to be put inside an Ethernet frame. But more about this later. Packets are sent one after another, but they don't all necessarily take the same route to their destination, nor do they necessarily arrive in the order that they were transmitted. If part of the network is particularly busy or even out of action, a router may decide to send some of the packets in different directions. For various reasons, perhaps electrical interference or a faulty device, the data inside a packet might get corrupted on the way. If so, this will be detected on the receiving computer. The protocol on the receiving computer recalculates the checksum for each packet using the packet data. If the result of the calculation is the same, it can be assumed that the packet arrived intact. If not, a request to resend the packet will be issued. There are lots of benefits to physically segmenting a network like this, not least greater resilience and improved security. TCP/IP is actually a collection of several different protocols, but the core functionality of TCP/IP comes from two separate protocols working together: the so-called Transmission Control Protocol, TCP, and the Internet Protocol, IP. The job of the Transmission Control Protocol is to break up the data from the sending computer into small packets and get these packets ready for transmission. Each packet is given a sequence number at this stage. The content of each packet is used to calculate extra information, which is then added to the packet as it's being created. The calculation is done again at the receiving end to check for corruption during transmission. TCP on the receiving computer reassembles the packets in the correct order according to their sequence numbers, and if there are any packets that have been damaged on the way or haven't been received at all, TCP will request that those packets be sent again. You can see then that Transmission Control Protocol is all about ensuring the integrity of the data. The Internet Protocol, on the other hand, will add addressing information to each packet, information to identify the intended recipient of the packets. This is the recipient's so-called IP address. The IP address of the sender is also added to the packet. The IP addresses also indicate where the recipient and the sender are located. This information is used by the network routers to ensure that the packets are sent in the right direction. So that packets can be routed correctly, each computer using TCP/IP must have an IP address that is unique on the network. This is actually a 32-bit number, but because this isn't easy for people to work with, it's divided up into 4 groups of 8 bits, known as octets. Then, each octet is written in base 10. The IP address can be entered on each computer individually, which is known as static configuration, or an IP address can be given to a computer automatically by a server when the computer boots up. This is known as dynamic configuration and is done by a separate piece of software known as DHCP, Dynamic Host Configuration Protocol. As well as an IP address, each computer is given another number known as a subnet mask. This is essential information for routers because it's used in conjunction with the IP address to identify the subnetwork that a computer is located on. A third piece of information a computer should be configured with is the IP address of a default gateway. The default gateway is the router that packets will be sent to if they're bound for a different subnetwork. Each router also has a default gateway, which is the next router it will forward packets to if it doesn't already know a better route. Most computers these days still use 32-bit IP addresses. These are known as IPv4 addresses. But IPv4 has a serious limitation. Because it's a 32-bit number, there are only about 4 billion IP addresses available. On a private LAN, this isn't an issue, but on the internet, it's a real problem. Every computer using the internet has to have a unique IP address. Not so long ago, about 4 billion was plenty, but the inventors of IP didn't anticipate the rapid way in which the use of the internet would grow. To work around this very real shortage, technologies like DHCP and proxy servers allow IP addresses to be issued only when necessary and to be shared between computers. But even so, the Internet of Everything continues to grow at an explosive rate. There's a new version of IP addressing available now, IP version 6, and people are gradually switching over. An IP version 6 address is a 128-bit number, allowing for 340 undecillion IP addresses. With that many, you could assign an IP address to every atom on the surface of the Earth over 100 times. For readability, an IP version 6 IP address is written as 8 groups of 4 hexadecimal digits, separated by colons. Now let's say a little about some of the other protocols in the TCP/IP suite that collectively provide the data transport services used on the Internet. The Hypertext Transfer Protocol, HTTP, is used to deliver multimedia-rich web pages to your browser over the World Wide Web. The File Transfer Protocol, FTP, can be used when you want to transfer files quickly from one computer to another. SMTP is the Simple Mail Transfer Protocol. This is used when email messages are sent between mail servers. POP is the Post Office Protocol. This comes into play when you retrieve email messages from a mail server, so you can work with them locally on a PC-based application such as Outlook. The Internet Message Access Protocol, IMAP, allows you to work with mail live on the server, using webmail systems such as Hotmail or Gmail. Voice over Internet Protocol is specifically for transferring voice and video data over the Internet, allowing for telephone-style conversations. In fact, VOIP is itself a suite of programs. We've already spoken about Transmission Control Protocol, and we'll say more soon. The User Datagram Protocol, UDP, is a lightweight alternative to TCP. It's much less reliable than TCP because it doesn't perform any of the error checking, but it's much faster. This makes UDP suitable for applications where the quality of transmission isn't a big issue, such as live video streaming and online games. We've already spoken about IP, and we'll say more in a moment. The Internet Control Message Protocol, ICMP, does as its name suggests. It's used by routers to exchange status information and error messages, for example to report that a particular router can't be reached. Most TCP/IP packets begin and end their journey on a LAN using Ethernet. But IP addresses can only get packets so far. The last leg of the journey depends on each packet bearing the destination MAC address. ARP, the Address Resolution Protocol, allows one device to discover another's MAC address if its IP address is known. Once the target network segment has been reached, the MAC address comes into play. There are other protocols in the TCP/IP suite. The ones you can see here are the most well known. So, how do these protocols work together to get data ready for network transmission? Let's start with the data we want to transmit. This might be a web page being delivered by a web server to a user's browser, a file being copied from one machine to another, or perhaps an email message. To begin with, the data must be collected from the application software and formatted for further processing. The protocols that perform this task include HTTP, FTP, SMTP and POP3, depending on the nature of the data. Then the data is broken down into packets. A sequence number and error checking data is added to each packet. In addition, something called a port number is added to indicate the nature of the data and therefore the application it's heading for. Don't confuse this with a physical port on a device that you plug a cable into. Port 80 means that it's HTTP data, that is, a web page. Port 20 is FTP data and port 25 is SMTP data. There are many others. Port numbers are not only used by the receiving application, but also by routers to control the movement of certain types of data in a process known as port forwarding. Packetizing the data is the job of TCP. The source and destination IP addresses are added to each packet. This is essential information for the routers. IP addressing information is added by the Internet Protocol, IP, or ICMP if it's control information. Finally, the source and destination MAC addresses are added to each packet. MAC addresses are essential for Ethernet communication on a LAN segment. Each IP packet is now enclosed within an Ethernet frame. Think of this as a package inside a package. ARP is an example of a protocol that's important when performing this task. You'll hear more about ARP in a moment. Here you can see 4 distinct layers of software, each layer with a name according to the job of the software operating at that layer. The application layer sits at the top. Underneath this is the transport layer, then the network layer, and finally the link layer at the bottom. This is the so-called 4-layer model, or the TCP/IP protocol stack. The software at each layer can only communicate with what's directly above and directly below. The interfaces between these layers, that is, the rules for passing data from one program to another, are standardized and well known. This means that software from manufacturers like Sun, Microsoft, Cisco and the open source community can write new programs to slot in at any position, confident in the knowledge that their software will work with someone else's. So how does the Address Resolution Protocol, ARP, actually work? Imagine there are 3 computers on a small LAN with a single switch, but no routers involved. One of these computers wants to send some data to another using TCP/IP in conjunction with Ethernet. To begin with, the sending computer doesn't know the intended recipient's MAC address, only its IP address. It needs to discover this MAC address somehow, so that each TCP/IP packet can be put inside an Ethernet frame. The sender starts by broadcasting a special type of Ethernet frame called an ARP request. This is recognised as a broadcast by the switch because the destination MAC address is all Fs. Essentially, the ARP request is asking every computer on the LAN segment, who has this IP address? If it's you, tell me your MAC address. All of the computers on this LAN segment will pull a copy of the packet up into the network layer, where the target IP address can be examined by the Internet Protocol. The computer which owns this target IP address will send back an ARP response packet. This contains the requested information. Of course, it knows the MAC address of the original sender. It was on the ARP request. So the ARP response is properly addressed for Ethernet transmission. From now on, all of the packets coming from the sender have the target MAC address on them. They are properly addressed Ethernet frames, and the switch knows which way to forward them onto. Only the receiving computer will pull packets all the way up through the TCP/IP stack, unpacking, reassembling and formatting the data in readiness for the user's application software. Each computer on the LAN maintains an ARP cache. This is a list of previously resolved IP addresses which can be used to speed up future transmissions. This ARP cache is, however, flushed from time to time. When there are routers involved, things work rather differently. A router is a more sophisticated device than a switch. It has a routing table that contains information about the entire segmented network, including other routers. A router can therefore work out the quickest way to get a packet to where it's going based on the destination IP address. Dynamic routers learn from each other. They automatically configure themselves and use their own protocols to share up-to-date information about what's on the network. Here you can see 4 network segments. The sender and the intended recipient are separated by 3 routers. This picture is somewhat simplified. Imagine that every segment contains at least one switch with several computers connected to it. Not only that, but in a large modern network, each router could well be connected to several other segments and thereby several other routers. Now, let's suppose that all of these devices have just been switched on, so that all of their ARP caches are empty, and the routers haven't learned much from each other yet. The sender broadcasts an ARP request, and this is seen by all of the computers on the same segment, including router 1. The ARP frame is pulled up into the router's network layer, so that the destination IP address can be examined. By comparing the destination and the source IP addresses, the router concludes that the intended recipient is on a different subnetwork. Router 1 is the sender's default gateway, so it responds with its own MAC address. From now on, all of the data packets from the sender are inside Ethernet frames bearing the router's MAC address. But the journey has only just begun. As soon as the Ethernet frames begin streaming in, Router 1 broadcasts an ARP request of its own onto any connected network segment, including the segment that leads to Router 2. Router 2 examines the ARP request, it concludes that the destination IP address is on a different subnet, and, because it's Router 1's default gateway, it responds with its own MAC address. Router 1 replaces the MAC address on each frame it receives from the sender with the MAC address of Router 2. All packets from the first router are now heading directly for the second router. Router 2 also broadcasts an ARP request to determine the MAC address of the next router in the chain. Router 3 responds accordingly. Router 2 replaces the MAC address on each frame it receives with the MAC address of Router 3. All packets from the second router are now heading directly for the third. Router 3 broadcasts an ARP request, and this router gets a response from the intended recipient. It swaps the MAC address on each frame it receives with the MAC address of the target computer. All of the packets from this router are now heading directly for their final destination. As you can see then, on a large segmented LAN or WAN, or indeed the internet, the MAC address on each packet is swapped each time it hops from router to router. Each router maintains a table of routes to subnetworks, other routers and computers. They quickly learn the fastest way to get data from one place to another, and will try these routes first. Modern routers are self-configuring and share information with others using their own protocols. To summarise, a network protocol like TCP/IP implements the rules of data transmission. Routers are essential in a packet-switched network. They're responsible for getting packets to their destination using the fastest routes possible. A router maintains a table of information about the entire network, and it shares this information with other routers dynamically. TCP/IP is a suite of protocols, of which TCP and IP provide the core functionality. The various protocols are arranged in 4 notional layers, known as the TCP/IP stack. Programs operating in one layer can only communicate with programs directly above or directly below. Standardized interfaces between layers allow for greater interoperability between networking software written by different manufacturers. TCP is responsible for packetizing data before transmission, ensuring that the packets are transmitted without error and reassembled correctly at the receiving end. IP, on the other hand, is responsible for ensuring that packets are routed correctly to their destinations. Computers on a large segmented network need to be able to uniquely identify each other, and routers need to be able to work out where to send data. For this reason, each device on a TCP/IP network has a unique IP address. ARP allows TCP/IP packets to be sent inside Ethernet frames. It's a means by which the MAC address of a networked device can be obtained from its IP address. As a packet moves across a large routed network, the MAC address of the Ethernet frame that contains it is swapped at each router, allowing it to hop to the next router.